Hi guys, welcome back to my science studio. In today's lesson, we're going to take a look at two incredibly important forces inside the atom, the electrostatic force and the nuclear force. Understanding these two helps explain everything from why electrons stay in orbit to why some atoms become radioactive. So let's dive right in. Remember our golden rule in chemistry: opposites attract. And in the last video, we talked about the three subatomic particles inside the atom: protons, neutrons, and electrons. In the nucleus, we have positively charged protons and neutral atoms. And when you combine a positive charge with a zero charge, the net nuclear charge ends up being positive. So why do electrons orbit the nucleus? Well, because electrons have a negative charge and they are strongly attracted to that positive nucleus. That attraction, the pull between opposite charges, is what we call the electrostatic force. And just like opposites attract, guess what? Like charges repel. Positive versus a positive, repel. Negative versus a negative, repel. So it doesn't matter if they're both positive or both negative. If the charges match, they push each other away. But now we have a problem. If all the protons in the nucleus are positive and like charges repel, why doesn't the entire nucleus just blow apart? That brings us to our second force, and that is called the nuclear force. And you know what? The name gives it away. It acts in the nucleus. It's the force that holds protons and neutrons tightly together, even though all the protons are trying to repel each other. The way I like to explain it to my students is like this. Imagine your house is full of siblings who all have really strong personalities. Those are the protons. When you put all those strong personalities in one room, they're naturally gonna clash and push each other away. But then there's that one sibling who acts like the glue in the family, the calm one, the mediator. That's the neutron. And neutrons help hold everything together, just like they stabilize the nucleus. Now here's a question for you. Which force do you think has to be stronger? Electrostatic or nuclear force? You see, if the nuclear force weren't stronger than the electrostatic repulsion, the nucleus couldn't stay together at all. So yes, the nuclear force is stronger. But just because it's strong doesn't mean it's unbeatable. I mean, if you keep adding more and more protons, more and more of those strong personalities, the electrostatic repulsion becomes harder and harder for the nuclear force to control. This is why elements with really high atomic numbers start to become unstable. And if you recall, the atomic number tells you the number of protons. And once you get past about an atomic number of 83, which is around bismuth, the nucleus becomes so crowded with protons that the nuclear force can't hold everything together anymore. And when that happens, protons and neutrons get ejected from the nucleus. And when they escape, they release energy. That process is what we call radioactive decay. And so radioactivity is simply the spontaneous release of energy and particles from an unstable nucleus. Now, something to keep in mind is that not every atom does this, only the ones with unstable nuclei. These atoms are what we call radioisotopes. Now, all of this brings us to a really important concept that chemistry teachers love to test, and that's the idea of half-life. So, what is a half-life? A half-life is simply the amount of time it takes for half of a radioactive substance to decay. And decay is just a fancy way of saying break down. So for example, if you start off with, let's say, 100 grams of a radioactive element, one half-life later, you only have 50 grams left. What about after another half-life? You're down to 25 grams, then 12.5 grams, and so on. And to help you visualize it, I drew this little diagram here. Most textbooks will ask questions like, how much is left after a certain number of half-lives? All you really need to understand is the pattern, that every half-life cuts the amount in half again. So after one half-life, the amount of your sample that's left is a half. After two half-lives, a fourth is left. Why? Because half of a half is a fourth. After three half-lives, what's half of a fourth? An eighth. And it keeps going. Now, in the real world, scientists actually use half-life for some really cool things. For example, paleontologists. So, my dinosaur fans, this one's for you. Scientists use carbon-14 to estimate the age of ancient fossils. They look at how much carbon-14 is left in bones to figure out how long ago the organism died. I know, pretty cool, right? But because I'm a science fiction lover at heart, I gave this example to my students. If you remember the movie Back to the Future, Doc Brown tells Marty McFly that his time machine, the DeLorean, runs on plutonium. And when he does so, Marty starts freaking out. But why do you think? Well, because it's radioactive. But what does that mean, though? Now, before I keep going, please do not go around saying that in Dooley Science Studio, I taught you that time travel is real and that a flux capacitor is scientifically legit. Absolutely not. But this is a fun way to remember how important plutonium is. Now, if you grab your periodic table and find plutonium, you'll see that it's way down in the actinide series and has an atomic number of 94, way past our 83 is unstable rule from earlier. That means that plutonium is radioactive. And remember from our last lesson about isotopes. Isotopes have the same number of protons and electrons, but different number of neutrons. So you can have plutonium-239, plutonium-240, plutonium-244, different isotopes, different mass numbers, okay? The isotope we care about today is plutonium-239, the one used in nuclear reactors and atomic bombs. Scientists actually created it by bombarding uranium with neutrons in the lab. So yes, humans can make radioactive elements. Now here's the wild part. Plutonium-239 has a half-life of about 24,100 years. That means it takes over 24,000 years for just half of its decay. And doing so releases a lot of energy in the process. I mean, that stuff would stay dangerously radioactive for thousands and thousands of years. Plenty of time to power, say, a flux capacitor, if those actually existed. So let's practice this with a Back to the Future themed question. And it says, plutonium-239 has a half-life of 24,100 years. In the movie Back to the Future, Doc Brown starts with a 10-gram sample of plutonium to power the DeLorean in 1955. How much will remain after 72,300 years? Here's how I tell my students to do it. First, start with your initial amount, which is 10 grams. And now multiply it by a half raised to the nth power. So just like how it says in this formula, where n is the number of half-lives. But how do we find n? What you can do is you take the total amount of time that's elapsed, so 72,300 years, and divide that by the length of one half-life, which here they give you to be 24,100 years. When you divide the two values, you end up getting 3. That is your n. So it takes 3 half-lives when you go from 24,100 years to 72,300 years. That's what that value is saying. Now it's my favorite part. We're just going to plug and chug into this formula. So you take the initial sample, which is 10 grams, times 1/2 raised to the 3rd power. And when you plug all this into your calculator, you should have gotten that after 72,300 years, only 1.25 grams of Doc Brown's original sample will remain. And that's why radioactive elements hang around for so long. Their half-lives are massive. But before I go, there's one last thing I want to point out because teachers love to ask this. What we just calculated, the 1.25 grams, is the amount left. That's what has not decayed yet. But if the question asks you for how much has decayed, that's different. To find that, all you have to do is take the amount that you initially started with, so the 10 grams, and subtract that by the amount that's left, what you just solved for, which is 1.25 grams. And you should get 8.75 grams that's been decayed. So just be super careful reading the wording of the question. The amounts left and the amount decayed are not the same thing. Thank you guys so much for hanging out with me in my science studio today. If you want a separate video where we only practice half-life questions together, please drop a comment below and let me know. Don't forget to like, subscribe, and share this video with your chemistry friends. I'll see you in the next lesson where we will talk about how atoms bond together through ionic or covalent bonds.